Look, these are the exact questions asked in FANG interviews, and nailing them, that's how you get a 20x CTC. I'm your senior hiring manager today, so let's just skip the small talk and dive straight into this technical explainer screen. We are going to cover 30 critical interview questions, focusing heavily on architecture and production readiness. You'll want to stay sharp and follow along till the very end, because passing this screen is what strictly separates the junior developers from the principal engineers.
All right, round one. We're tackling questions 1 through 3, differentiating generative AI, predictive AI, and discriminative models. Honestly, if you can't clearly articulate what kind of model you're actually building, we simply can't move forward to the architecture phase.
So the core difference really comes down to the model's fundamental objective. While predictive AI forecasts outcomes, like, say, estimating stock market trends, and discriminative models learn decision boundaries to categorize data, like figuring out if an incoming email is spam, generative AI does something entirely different. It actually models the joint probability to synthesize completely new data distributions. It doesn't just label or estimate, it creates something that literally wasn't there before. And in a production setting, generative models require entirely different compute and safety guardrails precisely because of this unpredictability.
Okay, round 2. Questions 4 through 10. I need you to explain LLMs, tokens, embeddings, transformers, self-attention, multi-head attention, and their main bottleneck. Look, I don't just want you to repeat industry buzzwords. I really want to know if you understand how the engine fundamentally works under the hood.
Explain to me exactly how large language models process data. Walk me through the flow. It starts with tokens, right? Breaking text down into fundamental units like syllables or characters. Then we convert those tokens into embeddings. These are high-dimensional numerical vectors that actually capture the true semantic meaning and relationships of the text. Finally, we take those embeddings and store them in a vector database for rapid, similarity-based retrieval. It's basically a highly optimized filing cabinet for concepts. Now, the crucial leap in architecture was when transformers replaced older recurrent neural networks using self-attention and multi-head attention. That allowed for massive parallel processing of sequences. But as an AI engineer, you've got to acknowledge the elephant in the room, the major bottleneck. Attention mechanisms scale quadratically with sequence length. Think about the compute load. Doubling the context window literally means 4 times the compute. It's a massive, massive architectural constraint that you absolutely have to design around when building for scale.
Moving on to round 3, questions 11 through 16. How do you control output behavior using prompt engineering, zero and few shot learning, temperature, top K, and top P? Out in the wild, we need absolute reliability for our users, not just raw, unguided generation.
Walk me through these parameters and show me how you balance creativity and reliability. Temperature, for instance, adjusts sampling randomness. You'll want to keep it super low if you need the model writing highly reliable SQL code, but you'd crank it up if it's drafting, say, creative marketing copy. Top K limits the model to the most probable K tokens, which strictly prevents it from selecting bizarre, out-of-left-field outliers. Top P does something similar, but it selects tokens within a cumulative probability threshold. It's all about fine-tuning these very specific dials for your exact use case.
Next, give me some real-time examples of how you use zero-shot, few-shot, and in-context learning. Zero-shot relies entirely on the model's pre-training to generalize to unseen tasks, with no examples given at all. Few-shot involves providing specific, contextual examples right in the prompt to carefully guide the output pattern. As for in-context learning, I want to see you use it to strictly format outputs into JSON schemas. That is absolutely critical, because if the output isn't strictly formatted, our downstream applications will completely break when they try to parse the data.
All right, round 4, questions 17 and 18. Explain GAN architecture and mode collapse. We're pivoting to image synthesis here to see if you actually understand the classic failure states.
So, describe the adversarial loop for me. You've got a generator creating fake data, right? And it's fighting a discriminator that's desperately trying to spot the fakes. But what happens when the generator finds one single specific output that fools the discriminator every single time? Well, it just keeps making that one thing over and over. That's called mode collapse, and it is incredibly frustrating in practice. To pass this round, you've got to explain to me how you'd fix mode collapse using techniques like gradient penalties or mini-batch discrimination to force the generator to actually create diverse outputs.
Halfway there, round 5, questions 19 through 22. Compare RAG, fine-tuning, LoRa, and mixture of experts. Tell me, how do you customize and scale these massive foundation models cost-effectively? Because remember, we do not have an infinite compute budget to just throw at our servers.
Comparing these two approaches is absolutely vital for any architect. Tell me why you would use RAG for a company's internal wiki, but fine-tuning if you wanted the model to speak specifically in a certain programming language. Well, RAG connects the model to external, up-to-date facts without touching the parameters at all. It's essentially an open book test. Fine-tuning, on the other hand, actually updates the internal weights. It permanently changes the model's fundamental behavior, tone, or dialect.
And, full fine-tuning is almost always way too expensive for rapid iterations. So explain to me how low-rank adaptation, or LoRa, freezes the base weights to train tiny adapter layers, which are often less than 1% of the total parameters. That drastically cuts down costs. Furthermore, I want to hear how a mixture of experts architecture routes tokens only to highly specific expert subnetworks. This massively lowers active inference cost while still letting you maintain a huge overall parameter count.
Let's keep the momentum going. Round 6, questions 23 and 24. Architect an end-to-end RAG pipeline and solve the lost-in-the-middle phenomenon. Grab a whiteboard marker because I want to see your actual system architecture for an enterprise-grade retrieval system. Walk me through the pipeline logic step by step. First up, semantic chunking to preserve context. Second, vector storage with really rich metadata. Third, a hybrid search that combines exact keyword matches with semantic similarity. Now, pay close attention to step 4. Explain to me how the cross-encoder re-ranking phase explicitly fixes the lost-in-the-middle memory issue that happens in million-token context windows. Basically, it does this by aggressively scoring and filtering out all those irrelevant noise chunks before they ever reach the generation phase. It's an absolute lifesaver.
Round 7, questions 25 and 26. Differentiate agentic workflows from chatbots and define AI memory. Look, everyone and their brother builds basic chatbots these days, but how do you build a truly autonomous AI agent? Break down exactly how an agentic workflow differs. A standard chatbot is totally passive. It's just query in, text out. But an AI agent, it actively utilizes external tools like web browsers, APIs, and code interpreters to autonomously execute multi-step planning to solve a complex goal. But here is the real test. If this agent runs autonomously for 3 straight days, how on earth does it remember what it did on day 1? That is exactly where vector-based long-term memory comes in, allowing for true context persistence rather than just relying on a short, fixed context window. Getting close to the end. Round 8. Questions 27 through 29. Define hallucinations, mitigation strategies, and LLM as a judge. If we deploy this system to millions of enterprise users, we absolutely cannot afford for the model to just confidently lie to them. Explain to me why LLMs hallucinate based on probabilistic token prediction. They're designed to generate what sounds plausible, not necessarily what is factually verified. Tell me how you would mitigate this using strict citation requirements and aggressive system prompts. And most importantly, explain how you would scale human evaluation using the LLM as a judge framework. This is where you deploy a massive teacher model to automatically grade the outputs of your smaller, faster production models for both faithfulness and tone. All right, the final round. Question 30. How do you ensure production safety and robustness using guardrails? To actually secure this job offer, you have to tell me how you prevent toxic outputs, prompt injections, and PII leakage in a live production environment, especially when bad actors are actively trying to break your system. Here's the truth. You simply cannot rely on the LLM to police itself. You must implement a deterministic safety layer, something like NeMo guardrails or Llama Guard, that sits strictly between the user and the probabilistic model. You use it to explicitly scan inputs to block prompt injections and scan outputs to catch toxic or hallucinated responses. And it absolutely must operate independently from the main model's generation process. If you can successfully build that safety wall, then and only then are you ready for deployment. Well, you survived the technical screen. You've proved you understand the core architecture, the production trade-offs, and the critical safety mechanisms required. But let me tell you, understanding the architecture is actually the easy part. The true test of a FANG engineer is bringing it to millions of users without bankrupting the company or leaking private data. So ask yourself, are you just playing with AI toys?